Okay, last time we discussed the second technique that I indicated to you as the main methods to derive small signal models of switch mode power converter, which is called the PWM switching average. Okay, so let me share the whiteboard. Okay, to apply this technique in order to derive the control to output transfer function of a buck converter which is operated in a continuous conduction mode, so CCM, which is the main operating mode of buck converters. Okay. Last time we employed, we learned that by using this technique, which is the PWM switch average method, we can have a, say, DC model, okay, for the switching network. Then we can also have a large, say, signal model that we can employ, for example, for, say, simulations by computer circuital simulators. And also we have an AC model, okay? And AC model, which is derived from this technique, is the model which is described in this page, okay? This is the AC model, okay? The model that describes what happens to the small signal variation. So we are, say, focusing our attention now to the variation of the variables in the switch mode power converter. And in this case, we, say, averaged and linearized our switching network, and this is the result of this analysis. Okay, this is the model of the PWM switch networks, and once we derive this model, we can apply it to all kind of converters we want to analyze, because for any kind of converter, we always can extract a network, which is called a switching network, which has an active, a passive, and a common node. Okay, and whatever is the, say, switch mode converters, then we can replace the switch network by using, for example, this model. Okay, so my goal today is to use these small signal models, the AC model derived by using this technique, for the buck converter. Okay, so here in this right-hand side of the page, you can see the buck converter, in which I highlighted in the red box the switch network. Okay, and so I also highlighted in orange the nodes that are the active node, the common mode, and the passive node. So my goal is to derive the control to output function, which is exactly this function here. So V naught hat versus D hat in frequency, using this small signal model previously derived. Okay, so what is our first step? To extract from the network this switch network and to replace the model we previously derived. Okay, so let's take this operation. Okay, so we have at the active node, we have the current controlled current source. Then we have our transformer which has a basic characteristic that it can transform also the DC. So the sign exactly tells you that this is not a real transformer. Okay, the turn ratio is 1 to D, and on the other side we have the voltage controlled voltage source, and this is the common node. Okay, and this is the passive node. Then this is the model. For the buck is particularly simple because the nodes are, say, in the same orientation and direction of the model. So to the common node we have the inductance, and so we can draw here the inductance. Then we have the output capacitor C0, the output load R. We are talking about small signal AC model, so the quantities are just small signal quantities. So this is V0 hat. The current here is IC at. The voltage here is called VCP at. This is L. Okay, L is already there. At the input side, we have input capacitor, which is C in, and then we have the input in. And this node, this current, is the current, sorry, this one, which is IA dot. VAP is here, indicated in this way. So we have replaced our switch network by our AC model, which is a small signal model. Okay, so we have to analyze this circuit now. Okay, and the same operation you can do for all kind of other converters. Okay, simply say replace in the same way you did for, say, I don't know, non-linear devices like diodes or MOSFET and transistor in, say, electronic circuit. Remember that we are talking about AC, say, derivation, AC environment. Okay, just looking at, say, the small signal variation of all electrical variables. So that means that, for example, the input voltage, which is V in, this is a constant voltage. Okay, and since this voltage is constant, in terms of small signal analysis, this quantity can be shorted. Okay, can be, say, neglected. So what is done here is to put the voltage at the input, say, like 0. Okay, since it's constant, is not, let's say, involved in small signal analysis in AC variable. What does it mean if I, say, put V in null? For example, look at this source, voltage source circuit here, which is VAP multiplied D. Okay, VAP in this circuit, VAP is the voltage across the active to passive node, so it is exactly V in. Okay, so what does it mean? That I have to, say, cancel out to short also this source here? The answer is, of course, not. This voltage source remain with this, say, voltage impressed VAP, capital letter, multiply D, small signal variation. If you look at this analysis, this is exactly what you do if you have, I don't know, a transistor, okay, a BJT. If you have a BJT and if you want to analyze, I don't know, the amplifications, okay, so quantities that are in the small signal environment, your model is something like this. Okay, base, emitter, and collector, base, emitter, and collector. For example, this is RP, and this is GM VBE. And GM is a parameter which is defined by IC divided the equivalent voltage. Okay, but IC is a constant value. It's derived from the, say, DC operating point. The same occurs and happens here. Okay, VAP is not null due to the fact that I have to put V in null. This is the V in voltage that you can have in your DC operating point. So these two sources here are something that you have to take into account without any modification. Okay, they take into account the DC operating point by this term IC, which is the current exiting the common node at DC point, DC operating point. VAP is the voltage across the active to passive node in the DC operation. Okay, so I just short Vin because in this circuit Vin is not considered, but VAP capital letter and IC capital letter just have to be maintained in their position. Okay, so this is our circuit. Look at what happens at the input side. You have a short, and so it means that the input capacitor is short circuit. The current source is, let's say, shorted. Okay, so another way we can redraw the circuit in this way. Here we have a short. Okay, no more input capacitance, no more current source because they are shorted. So what remains is just secondary side circuit. Pay attention, sometimes I use this symbol here for the dependent current and voltage source. Sometimes I use the previous one, which is something like this. Okay, so something like this. This is for the current source. This is for the voltage source. Other way, for example, this is another possibility. Or you can see this is another possibility. Okay, this is more international symbol. This is more, I can say, Italian symbol. Okay, so L, and then you have the output capacitor here, C0. Then you have the resistor, the load. Okay, and this is V0. So this is a 1 to D transformer, and so what happens if you have a 0 volt at the primary side of this transformer? That means that secondary side is null. So let me redraw by eliminating the transformer. Okay, C0 R, and then you have V0 hat. Okay, so this is the final circuit. Look that here I put Vin in place of VAP because VAP in this circuit is exactly Vin. Okay, so I can replace this. Vin is null in our derivation, but this is not null here for what I said before. Now I have to simply derive the small signal V0 variable looking at the circuit. Okay, but this is very simple because V0 is the source, which is Vin the hat that multiplies a fraction, and this fraction is as a numerator, which is R in parallel to 1s C0, R in parallel of 1 over S0 plus SL. I used Laplace here to say make this computation, but this is admissible here because we have at this point a linear time invariant circuit. Okay, this is the final result of my derivation. I first averaged the system, then I perturbated the system, then I linearize it. Okay, and when I linearize it, then at the end I have a linear time invariant circuit, which I can apply all the linear techniques to solve circuits, Laplace, superposition, etc., etc. Okay, so I use Laplace, and this is correct. Okay, it is not correct to apply Laplace in time, variant circuits or nonlinear circuits. Okay, so we have V0 over D. This is Vin. This is very simple because you have the parallel, and then what happens is that you have 1 over S square L C naught plus S L over R plus 1. Okay. So as you can see, I derived the control to output transfer function in a very few steps, and very simple because I just made reasonings about the circuit. Okay, I derived a model which is a circuit model for AC, and then I applied to the circuits. Say no differential equations, no matrices, no, let's say, cumbersome or, let's say, difficult derivations. Okay, so it's very simple. Let me just discuss another point. Remember what happens in the state space averaging method. In that case was the boost DCM, okay, boost CCM, sorry, if when I put the ESR, okay, if you put here the ESR, then I have to restart all my computation from the beginning. And the computation now with the ESR included are much more difficult than before. I have to write, say, another equation, which is the output equation, the Y equations. I have to rewrite all the differential equations that now can be a little bit different due to the presence of ESR. And then I have to make all the derivations, say the linearization, etc., etc. Now, what happens? I put ESR here, but now I can derive in just a single step the output voltage, okay? Because if you look at the circuit, then you can say that V naught, small signal, is again V in multiplied D, which is the source, okay, here. Then we have the same, say, partition that we have before, but then the output capacitor C naught has an ESR in series. So we have something like this. At the numerator, R, which is in parallel to 1 over C naught plus the ESR. At the denominator, R in parallel to C naught plus ESR plus SL. Nothing more than this. And if you compute these two parallel terms, you can get the new control voltage, the new control to output transfer function, which is V in multiply with 1 plus S C naught ESR at the numerator. Then we have S square L C naught 1 plus ESR R plus S L over R C naught ESR plus 1. Okay, of course, now we have the influence of ESR both at the numerator and the denominator here. Okay, so this is the correct version. Then what we can say that typically, and this is always happens in a practical situation, that ESR is always less than R. Okay? R is the load you can put at the output of your converter that exploits the DC voltage of the converter. ESR is something which is parasitic in the output electrolytic capacitors. So that means that this is always true. And so I can have this quantity to be 0. And the other situation is that the time constants L over R typically is much larger than C naught ESR, okay? Because ESR is very small, okay? So it means that also here you can see that this is nearly close to 0, okay? So this is also rewrite in this way. We have a numerator and then a denominator, okay, multiplied V in. Okay, this is my control to output transfer function for the buck CCM. Let me analyze a little bit further these expressions. Okay, so first of all, we can say that here you have a 0. Okay, this 0 is a left and plane 0, so that's good 0. Okay, then you have 2 poles, and you have 2 complex conjugate poles, and as you can see here, the frequency of these poles is 1 over 2 p square root L C naught. Here the 0 is the 0 of the ESR, so sometimes you can call also F ESR are 1 over 2 p C naught ESR. So the poles are now fixed. Fixed means that they do not move. Remember what we derived, what we found out in the boost CCM with the state space averaging derivation, that the poles are moving because they depend on the duty cycle, depends on the resistance. Okay, now the poles are fixed, so they are not moving. Of course, also the 0 is fixed because it depends only on C naught and ESR that are fixed. Okay, so this is fixed. Okay, so this is the reason why the buck is is typically operated from a few kilowatt to, let's say, megawatt applications in CCM, because the transfer function, the control to output function is very, say, is very good. It's very, say, something that can be managed in a good way without too much problem. Okay, this not happens for the boost CCM. In fact, the boost CCM is operated in DCM, discontinuous conduction mode, to avoid all that problems. Okay, so for the buck CCM, you have a 1 0 and 2 conjugate poles. Okay, look at this term here. This is the transfer function, the control to output transfer function at DC. So when S is 0. So this is the term that we call the gain. Remember then when we derive the buck parameter, we have that the variation of the output voltage versus D is exactly V in. This is the gain. Okay? Now this term can be regarded as the DC value of the control to output transfer function. This is exactly what we already derived previously in the buck steady state operation. Okay. At the end, we can say summarize all the transfer function we derived because they are very important. Okay. So by now, remember that the buck converter has 1 0 left and plane, good 0, then 2 conjugate poles at 1 over 2p square root of L C naught. The gain is exactly V in. So the gain depends on the voltage at the input. So it changes, changing the voltage V in. Okay. So as you can see, this PWM technique is very powerful. Okay. Just put your, say, small signal or DC model into your converters, and you can derive all the quantity you are interested of. You can also use this model for, say, analyzing some details of the operation. I want to give you just 2 very, say, short example that use the switch network, the pulse width modulation switch network averaging method, to define some details that otherwise will be very difficult to find out. Okay. So just to show you how this model can be powerful with respect to, for example, the state space averaging techniques. So let me analyze by using the pulse width modulation switch averaging technique, which is the impact of an input filter on, for example, the stability of the buck operated in CCM. Okay, so my goal is here that what is the impact of the input filter to the stability of a CCM operated buck. Remember that I mentioned it in the earlier lectures, this course, that typically any converters has always coupled to filters that are employed, that they are typically low-pass filters, employed to confine all the noises, the electromagnetic noises they generate into the converters, not to exporting, say, to surrounding equipment and circuits, okay, in order to avoid interference, malfunction, etc. of all the equipment that are in the same environment, okay? So if you have a buck converter, like this one I'm drawing here, I just put C in as the simplified form of any complex input field, okay? But the filter that you can have at the input can have this way, this shape, for example. You can have an L filter, then you can have another capacitance here, another C filter. They can have more of these, say, they are called P stage of the filter. Okay, then you can have more, say, cells in cascade. They can be also have a different architecture. But anyway, there is something that can be connected at the input side in order to filter out all the electromagnetic noise, the interference that are generated by the switching action of the diode and the switch. Okay, so something which is, say, can be designed for each case, but typically they are connected at the input side. Okay, so without entering too much details about the topologies of this filter, etc., what we can learn about this connection, then if you have the voltage source V in, the voltage source V in is always coupled to a, say, impedance. Okay, so you have V in, and this V in here has an impedance. Typically, this is a reactive impedance. Let me call, as I did in the slides, the impedance of the EMI filter, okay, zeta EMI, okay, which is the impedance, for example, of this network here, okay. Then we have the converter, okay. So the switch. Then we have the diode. Then we have inductor, etc. So I just considering this input filter here, which is described by this impedance, okay? So what is the impact of the presence of this impedance on our buck CCM? So if you want to analyze the effects, sometimes this can be difficult and say in order to analyze exactly what happens, but in order to say just have a first order approximation analysis, then we can apply the switch average techniques, okay, in order to see what happens. Okay, so let me again replace my switch network here. This is the switch network by its small signal average model that we previously derived, and see what happens. The analysis is somewhat similar to what we did before, but now we have an impedance at the input. Okay, the impedance is zeta EMI. Here we have the active node. The active node, you have the current source. Then you have the transformer. And then you have the passive node here and a common node here. So you have P. This is V, A, P multiplied the small variation of D. This is I, C, and D hat. Then you have inductance, L, and then you have the capacitance, C naught. Load. Okay. Again, I'm just talking about the small signal circuit, so the small signal analysis. Okay, this is my AC model of the switching network. So what happens that I have to put the input source, which is DC source, to 0. So V in equal to 0. Okay. So now we have this circuit here. Okay. Now I cannot say short circuit the current source because now we have this zeta mi impedance. So this is not possible. But we are in an environment which is linear and time invariant. Okay. This is a linear time invariant circuit. And in the same way we can apply the Laplace transformation, then we can apply also the superposition. Okay. So apply the superposition principle. Okay, the superposition principle states that you can find out your, say, solutions just by applying one source at a time, okay? Considering the other source to be switched off. And so we have to say we can apply this principle here. Let me consider first the voltage source, and so to put IC D equal to 0. And if you do this, I have something that is, of course, when you put a current source to 0 means that it's an open circuit. So I can replace it by an open circuit. So this is the rest of the circuit here. Okay, now my output is not more V0, is V0 prime because it's due just to a single generator. You can also say reflect this source here to the secondary side, okay? And when you do that, you have to multiply by the turn ratio squared. So this means that you have zeta EMI multiplied D square that can be put in series to the source, the inductance, C naught, and R, okay? I just take this EMI impedance and I put on the secondary side. And in order to do that, I have to multiply it by the square value of the turn ratio, which is T. Now, how can you analyze this circuit? Well, it's a simple circuit, and it's just important to analyze what happens here. That I don't want you, say, derive in details to analyze in details this kind of situation, because just an example of the powerful of the method is that I can see the following. I can carry out the following considerations. What happens if D hat increases? Okay, D hat is, let's say, means that my voltage here, this voltage source, is increasing. Okay, so if D hat is increasing, it means that this voltage source has a voltage that increases. And so this voltage is applied in order to derive V naught prime hat here. Okay, but if this source is increasing, it means that also V naught prime is increasing. So this means that V naught prime is increasing, of course, because this is the series circuits in which you have, say, to derive just V naught. So it's quite a partition, say a voltage partition. So if the source is increasing, the partition also increases. Okay. Now look what happens if and this is what I can do in the next page, I have VAP D naught equal to 0. So I'm applying the superposition principle, so I have to apply one source at a time. In this case, I have zeta EMI here. Now my current source is, say, in place, is ICD. I have the transformer, turn ratio, which is D. I have no more the voltage source. I have just directly the inductance, and then I have C naught and R. And this I have the short. Okay, so this is my circuit. Of course, this is not V naught hat, is V naught second. Okay, that obtained by using the other source, which previously was put to, say, to 0. So what happens here? Now the same consideration can be done here. What happens if D hat is increasing? If you look at the circuit, it means that if D hat is increasing, then the current, which is the current impressed by this current source, is increasing. Okay. If I increase this current here, it means that I derive in this, say, much higher current from the primary. Okay, it means that much current has been drawn from the primary side. Okay, so it means that much more current is absorbed from the primary. So that means that much more current is absorbed here from the, say, the secondary side. Okay, because they are linked in a transformer. Okay, so this current is increasing. This current is increasing in order to make the current source, say, impressing a higher current. But if this current is increasing with this direction, so from the right to the left, it means that more current is, let's say, the current that flows in that direction. Okay, so it means that now the contribution of the output voltage due to this source is decreasing. So you have two different, say, direction by which the two sources are working. Okay, the voltage source is working for an, say, increasing duty cycle in order to increase the output voltage. The current source, increasing the duty cycle, operates in order to reduce the output voltage. So they are two totally different behavior. So think what happens if this behavior, okay, occurs in different frequency ranges of operation. For example, suppose that in the high frequency range of operation, the contribution of the current source is dominating that of the voltage source. Okay, so this is an hypothesis. Okay, high frequency, the behavior that dominates is that of the current source. Okay, and in the, say, low frequency range, dominate the behavior of the voltage source. So we can conclude that there is a low frequency range in which the output voltage is increasing, okay, the contribution of the IC small signal is increasing, and an high frequency range in which the output voltage is decreasing. But now you should remember what we said, I think in the first lecture in this modeling part of the course, when we talked about the, say, right half plane zero. Okay, remember that if you have a right half plane zero, something like this, okay, if you have low frequency behavior, so that means that S is very small, okay, then you have that, say, this function here is more or less 1. At high frequency behavior, so omega S is very large, that means that this is -1, okay, because it dominates this part in terms of, so there is a change of sign due to this right half plane zero. But this happens the same, okay, because there is a low frequency range in which you have a specific behavior of the output voltage. And at high frequency range, we have that the output variation change the sign, reverse its sign. So it's, let's say, decreasing. So the input as a consequence of this, let's say, reasoning, which is a first order, let's say, approximated analysis of this effect, is that the impedance of the VMI filter can induce a, let's say, instability problem due to the fact that its behavior can be, let's say, similar to that of a right half plane zero. Okay, so as you will know, this can lead to, say, instability problems. Okay, this is a real important problem? Okay, typically this not happen so often. Okay, so the impedance of the MI filter placed at the input, it rarely induces instability of your converter. What it most often occurs is that you can have a, say, phase margin of your closed loop system which is lower respect to what you are expecting due to this problem. But some is very in a very few situations this can lead to instability. Okay, but the problem can be analyzed by using the, say, switch average method, the pulse width modulation switch average methods, as I did in this way. So this is the proof of the, say, powerful techniques that is the PWM switch network. Okay. You have questions about this kind of say analysis? I just want to give you another example of this, say, importance of this technique to, say, make some first order analysis of your circuits. And in this case, the analysis is, the example is about the ESR of the input capacitor. Okay, up to now we considered the ESR in terms of, let's say, power dissipation, in the sense that if you have electrolytic capacitors, then the current flow into these electrolytic capacitors it ups the capacitor due to the presence of DSR. Okay, DSR is an important parasitic element in series with an electrolytic capacitor that is responsible for, say, eating up this capacitor. So, in order to avoid some, say, heating problems, that you have to choose correctly your ESR, for example. Okay, and so this is the reason why in our previous analysis, steady state analysis, we derived the, say, root mean square value of the current in the input side and the output side, because this is a parameter that you can use to, say, buy your input and output capacitor. There is another problem that is due to the ESR and specifically to the ESR of the input capacitor. Okay, let me show you this case. Okay, again, supposing that you have a buck, and so you have the switch, you have the diode, you have the inductance, again C naught R. Okay. Let me just focus the attention on the ESR of the input capacitor. So that means that the output capacitor for me now is something which is without any ESR. Okay, so C in, and then you have ESR of C in. Let me discuss this case by using the PWM switch model for DC. I can do the same for the AC model, for the small signal model, but it's a little bit simple to analyze in DC. So let me analyze simply this model in steady state, if you want, in DC. Here you have the source. Okay, the source is something which is a real source. Okay, so real voltage source means that the source has an impedance, okay, in series. It's not simply a battery without any kind of series impedance. So looking at this side, you can see the voltage source, the battery plus a equivalent resistance or impedance in series. Okay, for example, that due to the filter, etc., etc. So what happens to the input voltage? So let me call this voltage here as V in, okay, as usual. For example, when the switch is off. Okay, when the switch is off, it means that no current flowing here. The current is null, and so the voltage V in has some value. Okay, and the value is this one. Let me call this value V2. Here the switch is off, so the diode is on, if you want. This voltage V2 that appears at the input side is a little bit higher than that you can have, say, without any ESR, so without any, in our, say, steady state analysis that we previously done in the previous lecture. Okay, suppose that this is my voltage V in, average value that we have previously analyzed. Is a little bit higher due to the fact that, say, this voltage here is something that, say, no current flowing here, and so all the current provided by the source flow through this ESR, say, flow to these input capacitors, and this means that you have this voltage V2. Compare this situation when the switch is closed. When the switch is closed, now the current here is no more zero, so there is a current flowing here. This current that flows here means that you have less current flowing through the C-in capacitors. Okay, due to the presence of the on switch, the current flowing to the input capacitor is a little bit lower, and so that means that your input voltage is, let's say, a little bit lower than that. Let me call this voltage V1. Okay. This is typical. This is what happens when the switch is on and the diode is off. This is a situation that is due anytime you have something that loads your signal. Okay, this is called the loading effect. Okay, there is a load here represented by the switch which is closed, and this is a current here, and the current which, say, now has this direction. Okay, this current, let's say, draw some partial current from drawing into the input capacitor. Okay, so it absorbs some current and avoid that it increases the input voltage. So the input voltage, due to the presence of DSR, is not exactly constant as we think in our steady state analysis. It's something that has, let's say, a periodic, this is TS, effect. Okay, so it's something that bounces from V1 and V2. what happens that when we have, let's say, the switch which is closed and the diode which is on, this voltage appears exactly here. Okay, this is V1. Okay, so this is the voltage which is responsible for the output voltage V0. Okay, so when we close the switch, it's like a sample and holds that always sample the voltage when it is at the lower value V in. So V2 is not something that can, say, be applied to the output, because when the V in occurs only when the switch is closed, and only when the switch is closed, this voltage V in is, let's say, something that charges the output filter. Okay, so instead of having the voltage V in practice, we have a voltage which is always lower, V1. Which is the difference between V2 and V1? The difference is due, say, in practice, to the presence of the ESR resistor here. If you have no ESR, so you have a short circuit here, then the input voltage is always, let's say, constant to the voltage V in. Since we have now the ESR, let's say, what happens that this ESR is responsible for this difference here. This is V2 minus V1. So ESR, and the current that, say, flow to GSR, making this difference, is the current that flows here. Say, this is the common node here. Let me call this current IC. Okay, when the switch is closed and the diode is on, is the current IC, which appear here, and multiplied by ESR gives you this difference here. So this is this difference here. The voltage between these two nodes, let me call A as usual, and P here, is VAP. We are in steady state, so in DC, so this is the average value I'm interested in, VAP, and VAP is the average of this voltage here. So we can say that it is V1, and V1 is the voltage applied when the switch is on, so during T on. And during T on we have D multiplied Ts plus the voltage V2, which is obtained when you have the switch is off, so during the time interval T off, which is 1 minus T multiplied Ts. Since we have to get the average, okay, you get exactly this expression. Now, V2 from this quantity is V1 plus ESR multiplied IC. I can use this V2 here inside this equation. So I can say that VAP, this value, is V1 multiplied D plus V2 V1 plus ESRIC 1 minus D. Okay? Let me get a simple manipulation of this expression. V1 plus V1D, V1 minus D here. Okay, let this simplifies. So we have just V1 multiplied 1 plus V2, ESR, IC 1 minus D. So we can say that V1 is VAP minus ESR IC multiplied 1 minus D. This is V1. Okay. Now, so this lower value here. We get VAP. Look at VCP. So the voltage at this common passive port. Okay, VCP according to our DC model, VCP is VAP multiplied D. And remember that we have this model here in DC. This is A, B, C, VAP, and VCP. So VCP is exactly VAP plus D. Okay. VAP is exactly what we call V1. Okay. Is this one. Okay. So is VAP minus ESR IC 1 minus D multiplied D. Now, this expression we derived in this way is simply something that has an immediate circuital, representation, let me say. Because this means that I have VCP, which is equal to the summation, okay, of two quantities. So that means that there are two quantities that are in series. This second part here is ESR 1 minus D multiplied D that multiplies IC. The current here is exactly IC. So that means that I can represent this expression like a resistor. So my circuit becomes something like this. I have VAP, and at the secondary side here you have the transformer, so VAP multiplies D, and then you have a resistor, and this resistor is ESR D 1 minus D. Inductance C naught, resistor. And here at the input you have a Cin without ESR. So in other terms, I employed this technique, which is the switch averaging technique, to move the original ESR of Cin here, which is here, to the secondary side of my model at the C. Because here now disappear from here, no ESR. The ESR is at the secondary side. Why is important this kind of computation? But in practice, you can do, you can evaluate, for example, the impact of ESR of your output voltage. Or maybe you just can compute your dissipated power. The dissipated power is the product of the resistance, ESR 1 minus D, multiplied the DC current flowing through it, okay? This is, let's say, constant current, and so the root mean square current is the same of the DC current, so the expression for computing the conduction loss of this resistance is exactly this one. And if you look at the ESR, okay, you can recognize that this part is a current that multiplies to the ESR gives the dissipated power. In other terms, this can be equal to the root mean square current square of the input capacitors. And we can say that this is IC, but IC average value is I naught multiplies D 1 minus D. And I derive something that I already derived, okay? If you look at the back steady state derivation, we derive the root mean square value of the input current, okay? And this root mean square value was computed by looking at the waveform, applying the definition, etc. In this way, I obtained the same exact results, which is this one. Okay, just say using this kind of analysis made by, say, applying the switch mode, the switch average techniques. So this is just an example, okay? An example of application to the circuit that can be, say, employed to derive something that we can also derive in some other way, okay? But just you focus your attention that this is a very powerful method, and then you can, say, apply for, say, different analysis that you can want to perform, okay? So this was the goal of this kind of applications. Okay, you can apply the AC model of the DC model, and this can be done. Okay, Simonetti, it should be switch on and the off first. Let me just see what I written, because it's easy that I make some, say, errors in the graph. No, that's correct. V2 is maybe in the slide. You refer in what happens in the slide. Let me check what it's in the slide. Because maybe in the slide. The slide is not correct. This is the opposite. Switch on. It's impossible to have switch on, and this is the switch off. When the switch is on, you have a loading effect. Okay, you are drawing current, and this current is not flowing into the ESR, and so the voltage is reduced. Okay, when of course the switch is off, then all the current provided by the source goes to ESR, so the voltage is increasing. Okay, so sorry about that. This is not correct. Okay, is correct what is written in the slide. So this is the second method that we analyze in order to see, say, what happens, the control to output transfer function. Remember that my final goal is to design the controller. Okay, so I just put something which is the details the working by using this method, but do not forget that my goal is to design the controller, something that we can start from tomorrow, okay, and in the next week. So tomorrow, the first hour, 8:30 up to 10, I conclude the third method description to derive the small signal model for the buck converter, boost converter, etc. And then from the 10 to 11:30, the second half of the tomorrow lecture will be devoted to start the analysis of the controllers, okay? So let me start with the description of the third method that you can apply to derive the small signal of switch mode power converter. We saw the state space averaging techniques, mathematical methods, always correct if you draw in the correct differential equation, but maybe somewhat longer, complicated, etc. Then we saw the switch average method, or the PWM switch averaging techniques. That is basically as a procedure, okay, like the state space, because you have to, say, derive the averaging model, then you have to linearize, but is a more circuital method, okay? So there is a procedure, but you can apply this procedure directly on the circuit. There is a little bit more insight into the physical meaning of what you are deriving, and so it can be also simple. Pay attention that both these methods works well in CCM, continuous conduction mode, and in effect I derive the boost CCM control to output transfer function, the buck CCM control to output transfer function. When you look at the DCM, they can be, let's say, a little bit more difficult. For sure, the state space averaging techniques, say, increase the difficulties in a strong way. Not so difficult, but anyway, it's much more difficult than CCM analysis for the switch averaging techniques. Now there is this another technique, which is called the circuit averaging method. This was the first method to be developed. Okay, this kind of method has not a codified procedure like the previously described methods. Okay, so it's something that is more or less a circuital analysis of your circuit. Okay, has not specific steps that are codified in order to derive what you intend to derive. So in this sense, sometimes you can go in the wrong direction and you can have longer, say, calculations. But let's say if you apply well the concept, you can always derive some good results, okay? But since there is nothing which is codified, so there's nothing that you can apply mechanically, then sometimes you can go in the wrong direction. Was the first to be derived, and since this is not a, say, fully codified method, there are no precise steps, etc. This is the reason why other people try to search for something which is more precise in the steps that I have to do, like, for example, the previous two methods. Okay, so of course, is always a matter of trade-off. Okay, more mathematically, totally, say, described in the procedure, but maybe sometimes longer. Totally, say, circuital, and so based on analysis of the circuits like this one, but sometimes you can wrong direction. And then there is something in between, which is the pulse width modulation switch averaging techniques that try to, say, combine bonded techniques, if you want. So what is the main feature of these methods? That when you look at switch mode power converters, any person understand that the problems, the time variant issue of this converter are due to the switches. Okay, so this problem was solved in different way in state space averaging techniques or switch averaging techniques. But anyway, what you have to do to solve this problem, so to move from a time variant environment to a time, say, invariant, is to average the electrical quantities in these switches. Okay, so this method works just on the switches. Okay, working on the switches, what is done here is to replace my switch with the average electrical quantities that they represent. For example, if you have a diode, okay, in any switch mode converter you have a diode, then this diode forces a periodical variation of the current flowing across the diode. So you can think to avoid the variant issues of this problem, the variable structure of these circuits, by replacing the diode with the average current in a period that it can impress to the circuits. In another way, you can also think about the diode something that impresses a variable voltage across it. Depending on the status of the diode voltage can be 0 or can be whatever else. So another analysis can be done in terms of the average voltage. So you can replace the diode with two different sources. A current average source, which is the measure of the average quantity of, in a period Ts of the current flowing through the diode, or an average, say, voltage source, which is the average voltage across the diode during Ts. The same for the switch. So it's not looking at the switch network and to find a model for the switch network, which is the combination of the switch and the diode. It's look just at the switching elements and try to put a current source or a voltage source, average quantities, in place of these switches. Of course, sometimes it is easier to replace the diode with a current source. Sometimes it's easier to replace the diode for the analysis with a voltage source. This is the reason why this requires a lot of experience in order to understand which is the more suitable model that leads to the correct result in a faster way. Okay, so it's something which is left to the designer capability and experience. Okay, this is not something which is, say, something that can be codified in a specific and strictly procedure. So when you look at a circuit like this one, okay, which is the buck boost, you can recognize that if you have, for example, a resistor, and then you take the average of the voltage and current through the resistor, no change happens to the component itself. The resistor remains a resistor. The same happens for the other linear component. Okay, if you have an inductance, this is the characteristic expression of the inductance. You can also average the voltage and the current to the inductance, but they are always related by the same L. And this happens also for C. So no change are made in the circuits for capacitance, for the inductance, okay, and resistors. The only variable structure issues are due to the switches. So, as I said before, I have to replace the switches with their average current or voltages. Okay, we have to replace the switches by, I don't know, voltage source or current source. Let me exemplify this procedure looking at the buck boost DCM, something which is not, say, easy to derive with other techniques previously evaluated, okay, but in this case can be easily done. Okay, so buck boost DCM. Remember that buck boost is something that is related to the boost. Okay, and so it has the same problem in CCM, the problems that I highlighted by looking at the state space average. Okay, the example I gave you in that situation was the boost CCM, 0 in the right half plane, etc. The same happens for the buck boost. Okay, so the boost and the buck boost are typically employed in DCM. Okay, basically the buck boost is the more employed converter in DCM. Okay, the boost is not so employed like, for example, the buck boost. So it's worth to analyze what happens in the buck boost DCM. Of course, the same conclusion that we get for the buck boost DCM can be applied to the boost DCM. So they are, in this case, are practically, they can have the same condition. So let me start just by looking at this buck boost DCM, and my idea here. Let me share the whiteboard. Here you have the buck boost DCM by circuit average method. Okay. Just focus what happens to the output side. Okay, so output side we have the diode. The buck boost diode has that polarity, C0, and the output. Okay. Let's analyze what happens replacing the diode with something that is the average of its current. Okay, the current is flowing here. And look at what happens to the average. Remember that the current in the DCM diode is something like this. This is TS. We have a first time interval, which is T1, in which the switch is on and the diode is off. So no current can flow in this period. Then you have another period, which is called T3 or T idle here, in which both the switch and the diode are off, so no current can flow here. The current only flows during T2. Okay, and during T2, this current is the same current that flows through the inductor. And it's something like this. Okay. which is the slope of this current here. The slope is V naught over R. Remember that V naught that has this polarity is negative in the buck boost. Okay, if you look at the current through the inductor is here. Okay, current through the inductor, IL, this current is something like this. Okay, it has the same peak value, Imax, and this slope here, the positive slope, is V in over L, the slope. Okay, so the idea is that in place of this current here flowing through TS, I can use an average quantity, which is this one. And when I find out this average quantity, I can replace the diode here with a current source. That impress a current which is exactly the average current. Okay, this is the main idea of this method. Okay, I have a variation which is, let's say, something time variant. Okay, let me replace this time variant component by a time invariant component, like for example a current source which has the current equal to the average value of the current flowing to the diode. Of course, the same reason you can do with the voltage. Okay, when the diode is on, the voltage across it is 0. When the diode is off, the voltage across it is, let's say, something that you can relate to the circuit voltages. And now in the same way, you can put here a voltage source. Okay, so you can put here a voltage source that has, I don't know, a voltage like here, which is the voltage equal to the average value of the voltage across it. So which one I have to choose? It depends. Okay, it depends. I don't know, basically, at the beginning of the analysis. Sometimes the wrong selection gives you, say, more calculation, etc. Okay, but of course, you always can get a result. In this situation, I can assure you that if you choose the current source, you can have less computation. Okay, so tomorrow we can start from this analysis. Okay, I have to find out the average value of this current, the current through the diode, and then with this average value, I can replace the diode with a current source with this current average. Okay. Okay, if you have questions, I'm here to answer your questions. If you have no questions, we can see each other tomorrow morning at 8:30. Okay? Thank you very much for your attention. Have a nice day.